Welcome to this video lecture on the subject electronic circuits. So in this lecture we are going to discuss about double tuned amplifiers. So what is the need for double tuned amplifiers? So for radio frequency applications for amplifier circuits, we need to select a particular frequency for the particular channel. So in that case we need the high selectivity and adjacent channel rejection. So and also we need to reduce the noise and distortion. So we need a improved signal to noise ratio. So these are the requirements of the amplifiers. So double tuned amplifiers are particularly used for higher quality factor and bandwidth. So what is meant by double tuned amplifier? So here the tuned circuit consists of two tuned circuits L1 C1 and L2 C2. It will be connected at the collector section of the amplifier. So let's see the circuit diagram for double tuned amplifiers. Here the basic common emitter configuration is used in this circuit, in which the input signal is given to the base of the amplifier, and at the collector of the amplifier tuned circuit is given, in which L1 C1 L2 C2 is the double tuned circuit. Here the input signal applied to the base of the amplifier is amplified and appears across the primary tuned circuit. Let's see the working in detail. The high frequency signal to be amplified. So as seen in the previous circuit diagram, that is at the output of the L1 C1 we can couple the double tuned circuit L2 C2. So here it offers high reactance to the signal frequency. So we get the output at the double tuned circuit. These double tuned circuits are extensively used for coupling various circuits like radio and television receivers. So what is the benefit of using the double tuned amplifier is that we need two coils. So coupling between the two coils given better selectivity, higher voltage gain and required bandwidth. So these are the benefits of using this double tuned amplifiers. And the mutual inductance concept is applied in this double tuned circuit. So when we are using the two coils, the EMF induced in the secondary coil due to the time varying magnetic field of the primary coil. So this phenomenon is called as the mutual inductance. So this is used in the double tuned circuit. So let's see the frequency response. So here two positions of gain maxima. For example, gain versus frequency is drawn. At a particular resonant frequency we have two maxima. So this is the tight coupling. So this will be achieved by using the distance between the two coupled circuits. And bandwidth of the double tuned circuit. The bandwidth increases with the degree of coupling. For example, we can write the bandwidth as K into Fr, where K is the coefficient of coupling. So this factor is the determining factor of the double tuned factor. So let's see the advantages and of double tuned amplifiers. For example, so comparing to single tuned amplifiers, so this double tuned circuit gives wider bandwidth, and also it provides higher gain because of increased amplification at the resonant frequency, and also it reduces distortion in the radio frequency applications, and better power transfer, provides improved impedance matching. So these are the advantages of double tuned amplifiers. And what are the applications of tuned amplifiers? So these are the circuits where IF amplifiers, television receiver circuits and RF amplifiers, these are the main areas to be applied for double tune amplifiers. So these are commonly used in radio receivers to process the signal before demodulation, and television receiver circuits for selective amplification of a TV signal. Let's take the assessment questions. So what is the typical frequency response shape of a double tuned amplifier due to the coupling between two LC circuits? So the answer is option B, a double humped or flattened response with sharp edges. In a double tune amplifier, the coupling coefficient primarily influences the shape and bandwidth of the frequency response. So thank you for listening this lecture.